We go from third grade to the hardest, perhaps the hardest section. little transition. So we're going to derive the Euler-Lagrange equation. And what that's done, that's what gets you from the back of the t-shirt to the front of the t-shirt. And in some ways I can't do this. I can only give you a sense of what it is. Don't try and say, yes, I totally get every single detail that's going on there. All right. So I have to explain what an action is. An action integrates the Lagrange density, that mass per volume, over space and time. Okay? And so the result is mass times time. And you go, okay, so I do this for a second, or I do it for a million years. I bet I get really different numbers. Why are you bothering me with this? It's not the action that matters. It's the variation on the action that matters. What I'm going to try and do is find something in here that I can change, and if I integrate over a second, that variation I did doesn't matter over that second. If I look over a million years, that variation doesn't matter. Okay? And this is actually minimization problem, as we had on the quiz. Okay, just a little bit more complicated. So let me give you three important cases here. If the Lagrange density is not a function of time, that means that energy is conserved. And I don't know, this seems like I'm getting deeper into, how nature works. Before I was like, yes, energy is conserved. But now it's like, well, I bet there's a Lagrangian in there, and I bet whatever the Lagrangian is, it doesn't have time in there. There's no e to the minus t that you might have if something was exponentially decaying, something like that. All right? If the Lagrange density is not a function of space, if it doesn't matter exactly, if there isn't a place to put the x, y, and z, then actually it means that space is a symmetry, and it means that momentum is conserved. And the third thing is, if you look at that Lagrange density and it's not a function of angle, then you're going to get angular momentum conservation. All right, so if we have a Lagrange density that depends not on space, not on speed, not on these things, but on a four potential A, and it also depends on derivatives of that four potential A, we're going to vary these things, and we're going to find minimum. And that is at the heart of the Euler-Lagrange equation. So here again we see we've got a Lagrangian, we're doing variations on that sort of thing, we're integrating over space and time, and we're saying, okay, let's get a minimum out of that variation. Okay, so this is my sketch of how to derive it. You start with that Lagrange density that's really only a function of A and the derivatives of A. You form an action, which means you add it all up, and you vary that action. You vary that action with respect to A and the changing fields of A. But this gives you a problem. The problem is, let me see if I can do it back here. The problem is that this is an apple and that's an orange. So how are you going to deal with the apple and oranges thing? And the way you deal with that is you use the product rule. And this looks a little crazy, because I think it is a little crazy. But that step four and five are where if you're in graduate school you get rock solid on how that all works. Okay, so I'm a little hand wavy here, but I think you get the product rule saying if I take this del on both of these things, I get just that acting on there. But there's a theorem of Gauss that says that this whole thing is actually equal to 0, and that can be the case only if those two happen to equal each other. And now we go, well, here we've got the difference, the variation on the fields, and here we've got variation on A. That's like the other one. So why don't I just plug this into that equation that was on the previous slide, and if I do that, I end up here, and it's all a variation on the field A. Okay, so that's good, because then I can say, well, if I really want 0, let's make sure that thing is 0. Okay, and that is Euler-Lagrange right there. Okay, so that's to give you a sense of it. Don't feel like you can go and do a proof of it, but that's kind of a sense of it. And then if you say, well, show me the details. Okay, this is what it is. If you were to write this all out, people are going to think you're brilliant, because it has so many partial differential equations. Okay, so along this side we're doing, these aren't so bad. This d phi, dax, day, daz. This looks like a nightmare until you go, well, there are patterns here too. Okay, that top line is all phis, then all ax's, then all ay's, then all az's. Okay, sorry, these guys. And then you notice that you get pairs. But you get a lot of them. And that's the nature of the game. So that is what we're going to use to derive the Maxwell equations. Once we have something to put into the Lagrangian. And that brings us to this. We can all agree on Lorentz invariance, even if we haven't taken special relativity. But special relativity is, in essence, it deals with Lorentz invariance most of the time. Okay, so the Egyptians figured out something we can all agree on. That 3 squared plus 4 squared equals 5 squared. They used that with the rope thing so many years ago. It was useful math. I don't actually know whether the Egyptians figured out they can do the third dimension or not, but it's not that big a step out there. And it was Einstein in 1905 who modernized it and said if he was in a rocket ship going by here, you know, the lengths would change, the times would change between the measurements, but this thing is called an interval. If you calculated that, everyone would agree to that number. So all it is time squared minus x squared, y squared, z squared. And that's called the Lorentz invariant interval. Okay. So if you were now moving like a crazy man all over the place, you could do this as long as you could figure out what the functions were of that crazy motion you were doing, that f and the h, and that's this kind of thing that general relativity allows you to do. As I say, only a few special cases, and I'm not going to force any on you in this over these 3 days. That is too hard. Okay, so that Lagrange density, that mass per unit volume, requires a Lorentz invariant numerator. And what you do with quaternions anyway is you just multiply it out and go, oh yes, that's the dot product, and it's got to have that minus because it's kind of like a complex number. And then otherwise it's scalar times a vector, and the cross product. So that's it. And what's amazing is that first term of any quaternion product is a Lorentz invariant scalar. And it is the reason I purchased quaternions.com in 1997. I was in the library and I saw, oh, actually it wasn't this particular one. It was t squared minus x squared minus y squared minus z squared right in the page, and I said, that's not luck. And I was so struck by that after taking a good course on special relativity and knowing how important the Lorentz invariant interval is that I bought it. And this actually, current coupling term actually is on the t-shirt on the back. All right. So the hypercomplex products that I talked about, you can actually make something that's Lorentz invariant as long as you add a conjugate operator in there. And now because Lorentz invariants are so important, I basically kind of team them up. I never take one of those products without also taking a conjugate. And this also appears on the t-shirt. Okay, so that's 2 out of the 4 terms actually on the T-shirt. It's this one and it's this one, but I had to somehow come up with the other 2, and I was struggling to figure out how I could teach this, and I realized all I have to do is mess it up. Remember, all you have to do is multiply 2 quaternions. You get a Lorentz invariant interval out. Well, what if I put a conjugate there? I messed it up. Is this bad news? I'm going to argue that eventually we'll see it's actually good news. Okay, so I get this scalar that's definitely not Lorentz invariant. It's got the plus sign and a bunch of other things, 3 vectors. Actually, well, anyway. So that scalar is such a problem. What are you going to do with a broken scalar? You throw it away. And so that's all you do right there. Take this thing, take its conjugate, and it goes away. So now what I have to do is make a Lorentz invariant scalar out of that. And that's kind of gets more tricky. But there are two types of 3 vectors inside there. There's there's the axial and the polar one. And the polar one has the property that if you change the order of it, you flip signs. So let's try and be complete in our analysis. This is always my thing. Let's be complete. Let's be complete with our multiplication. Let's be complete with looking at both sides of our cross product. So dA gives me one thing, and then if I flip around the signs, did I mess that up? I always worry about messing up my signs. All right. Yeah. No. Yeah. I guess I did it right. I was saying, why is that plus? It's because that was minus. So that's good. All right. So these 2 3 vectors, they point in different directions. Okay. But the thing is that their norms will be the same. So if I calculate the size of these 2 norms, if I take one vector that's pointing this way, and another vector pointing in that way, and I say, what are your norms? Now subtract those, I'll get 0. So that will work out. And so that's the idea, is 0 must be a Lorentz invariant interval. And you get this really, really nasty, complicated 3 vector, and I'm pleased to tell you guys that at least at this point, we don't have to analyze that. That would be scary. Okay. 0 is comfortable. I like 0. And in fact, this is going to be the key to the homogeneous equations. That, amazingly enough, is the B dot E sort of thing. And then, I don't know how to really prove this in a pithy way at this point. All I can say is at this point that if you take the 2 orderings and you form the product of that, then that gives you a Lorentz invariant, and that's actually going to be this b squared minus e squared thing that's going to go into the Maxwell source equations. So I think we're getting done with that one, which is good. So now we're going to actually derive some of Maxwell equations. Oh, and it's going to take a while, but hey, Max's work. All right. So, the basic strategy of deriving the homogeneous equations is to plug a Lorentz invariant into the Euler-Lagrange equations and go. So, what are the Maxwell equations? This is my big picture, step back, what is it all about? And so, it defines how a current density is the source of all changes in space-time, of four space-time potential. Okay? 4 particles that are traveling at the speed of light using quaternion multiplication. So this is really just like, I'm just being thorough. I'm not skipping anything whatsoever. What's completely odd, and no one else on the planet's going to say at this point, is this link to quaternions. Okay, and believe me, you can do this all without mentioning the word quaternions, which is usually the way it's done. Okay, so I'm going to construct a complete set of first-order changes in the potential. And how am I going to do this completeness? I'm just going to multiply this out. That's it, okay? So, and I can see that 3 vector there is negative the E field and the B field that we talked about so long ago on the quiz. We had that on the quiz. But let me just repeat this, okay? The most basic complete quaternion derivative is electromagnetism. It's like, I couldn't have made this up. You know, I just don't think that's luck. It's not luck rearing its head again. All right, so, but that extra scalar field is a problem. It's a problem because it won't, it's not actually Lorentz invariant. Okay, and if you're in physics grad school, you can probably say why that gauge field must be 0 so that things can travel at the speed of light. I certainly know of those arguments. I'm going to just say this is one of those times when I'm going to be a little hand wave, okay? And I'm going to say you can't have scalar gauge terms in your Lagrangian and travel at the speed of light. And what do I mean by that more in a concrete way? Because I'm a lunchbox guy. You can't have a dp dt, you can't have dAx dx, you can't have dy dy, you can't have dAz dz. And you'll notice that the thing about this guy, it doesn't have dphi dt. It isn't there. And there's this funkiness going on here when you look at it up close about i's, j's, and k's. And you figure out that I was just being crafty. I didn't want to write the ai, the xi. I wanted this to be invariant under gauge transformation if I want to sound very formal, which I usually don't. Okay, so we need an invariant. So we do what we worked out before, which was to say, I want to square that one of those guys, subtract the square of that thing. What am I going to get out of this? And this is that square of the things where one's a plus and the other one's a minus, and you basically get out E dot B out of that process. Okay, so we're going to now derive the no monopoles law, and we're going to start with one easy term, EX. Okay, then we're going to pair that with a BX, multiply that out, clone a bunch of lines. Actually, I should say we're going to Sudoku. I think I'll change it. Sudoku a bunch of lines and look for the resulting patterns. Okay. So we've got to write out every single term of E dot B. And it was scary. It is scary. When I was writing up these notes, it's like, how am I going to do this? Okay? I am going to start out easy. I'm going to write out EX. And I remember, oh, it's got a bunch of X's. Everything's negative, and it's like, okay, it's got to be kind of late. And then it's got to be something, all right? And a bunch of other terms that I'm not worrying about. I take the first step. This first step is simple. All right, so BX is everything not in EX. So it's got AY's in there, it's got AZ's in there, and it's got the other two derivatives, and the only tricky thing is remembering the signs. And you go, oh, I first make contact with AY and then AZ, and so then that flows out. All right? And you multiply this out. Okay? We've done this many times back in 8th grade or the 9th grade sort of thing. And when you do that, half of the terms are positive and half are negative, which is kind of nice because we know if this really is going to make it to the no monopoles law, we want a whole bunch of cancellations going on. Another cool thing to just see about it is like it's like every one of the 4 directions makes a contribution. So there's a thing from time in that first one. There's a thing AX. There's an AY. There's an AZ. The phi thing is like the time guy, and it's got an X. It's got a Y. It's got a Z. It's like we are all sharing. Isn't this beautiful? Okay. And so now what we do is we clone EX to make EY and EZ. So we haven't filled this stuff in because it'd be scary to write it all down at once. Okay? But it's not scary to write EY or EZ. Okay? Particularly when we line them up and go, oh, I can pull that in straight away. Now what do I do? Well, why don't I look for some patterns? And it's like, oh, yeah, I see two z's, I see two y's. It's like, that's very much like curl, okay? So what if I kind of like play what I call curl Sudoku? And this is actually formally curl Sudoku. This isn't like approximately, all right? That second line there, we know, since it's the y, it's got to involve a dx and a dz. And if we play Sudoku, I can't put the dz here. I have to put dz here. That means I have to put dx there. And this final thing has got a dx and a dy. And formally, it is, again, Sudoku. I can't put y's there. It would be wrong. I had to put y's here. I had to put x's there. I never thought, until I gave this talk, that Sudoku had a practical purpose. But here we are deriving the no monopoles law, and that's curl Sudoku. Okay, so we played it on that line. Guess what? I've got y's and I've got z's. I'm going to play the game again. And when I play the game again, I go, oh, my z and x. Oh, yeah, z had to be there. That puts x over there. And then this was ay, had to go over there, forcing ax right over there. And I think this is pretty. All right, this is our Lagrange density. Just take a step back again. This is Lagrange density. This is every way that energy can be exchanged inside of a volume involving B and B. And you notice that the E field is sitting right next to the B field. And all we have to do is take that, put it in the Euler-Lagrange, and we'll get the result. But people just aren't good at dealing with this much stuff. Actually, there are some people who are good at this sort of thing, and they scare us. Okay, so I had to make things much simpler than that, and it's much simpler to do things one at a time. Make them simple. Okay, so the first one is we're taking derivatives with respect to phi. And then we notice we've got this, all we have are phis. There's no ax, no ay, no az. And then we've got these pairs of derivative things going on. Okay, so let's look at our Lagrange density that we have, this E dot B thing. And, oh good, I get to ignore half the terms. I always like when I get to ignore half the stuff that's there. That's very good. But what am I going to do with the calculus going on there? Well, remember the quiz. We had, what's the derivative of xy over x? It's just y. But what if x is this complicated d phi dx? Well, it's just that complicated d phi dx. I mean, it's just a different way of writing x. And so if we end up with one of these things like that, we're going to, and then take the x derivative, we're just going to get the second derivative, and it's going to be a mixed derivative. So you can see, maybe I should have gotten that. But, you see, we've got these two, and they end up over there. And the phi goes away, and we just end up with a 2 over there. So it's not even hard to write down what the mixed derivatives are. Okay? So let's go back here and say, okay, so I can see I'm going to get an xy all the way up there on the top. I guess I can't do gesture too well, that's right. And then I'm going to get the same thing down here. It's just that they've got a different sign. And if you spend some quality time, there you go. Okay, one's a zy, the other's a yz. You can see there's this changing of order, but that doesn't matter. What matters is that they got different signs. These guys are all going to cancel. All right? You already knew that, kind of. Suspected as much. But what's cool is that if you now look at them line by line and say, what is that line? That line is, they've got an extra, they both have a dx in them. So if you pull the dx out, you go, oh, that's one of those B fields. So I'm basically taking the repeat for all of these things. I'm taking the divergence of the B field. And so that is how to derive the law. This is kind of a graphic which will give you a kind of more sophisticated appreciation of the no monopoles law. Because the cancellations happen across lines. But the del dot B, that's across the line. So, so that's kind of an interesting visualization. we're now going to try and derive Faraday's law from the same darn Lagrangian, okay? I'm not going to change it out on you. I'm just going to use different parts. What parts am I going to use? I'm going to look for everybody who has an AX. And it turns out, again, it's half the terms. But, let's see, yeah, half the terms. And you can see the red arrows show, oh, if I start taking, I'm going to get mixed derivatives here. I'm going to get a ty guy. I'm going to get a ty there, a minus and a plus. Oh, I'm going to get a tz up there. Oh, so you can kind of see cancellations going on between the plus terms and the minus terms. What's harder to see maybe is this take the curl of an E field, and I don't think this slide really summarizes that too well. I'm sorry about that, but that's, so that anyway leads to Faraday's law, and you get the cancellations. All right, let me see what I'm doing. All right, so this I call the forgotten way to derive the homogeneous equations. Because usually what they say is it's a vector identity. We'll give you a real simple explanation of how to do this, and you're done. And believe me, that is faster and easier than what I've just done. And you can use the tools of differential geometry to say this also in a very sophisticated way. And so nobody puts E dot B to much use. But I wanted to be, in essence, logically consistent. In other words, I'm always using Lagrangian because that's how energy can be changed in volume, and then I do this Euler-Lagrange to get out what I want. All right. So we're going to derive more. All right, more field equations, and we're always going to do the same darn thing. Okay. So I'm sorry if I get a little repetitive. Writing out the Lagrangian, writing out the terms of the Lagrangian, applying Euler-Lagrange. Take all the derivatives, collect them together, and then we'll have our statement. But we've done two, okay? We've got halfway. You're halfway home as far as Maxwell is concerned. So we will move on to derive the Maxwell source equations. Okay, so there we go. Again, we got to plug something into the Lorentz invariant into the Euler-Lagrange. Now this time we're going to do this b squared minus e squared. Now in essence, just to say, well, what is new and different about what you're doing? Only this first step is, okay, where I say I'm just going to take these guys and just multiply them together using math you knew in high school to get b squared minus d squared. Yes, I get something called the pointing vector, which shows up in EM. I get it for free, okay? It's like, people give a big, long explanation. It's like, no, just multiply it out. It's there. Nature uses it, okay, because you multiply this stuff out. So, but if I was in a more formal class, they would write out, they would write it this way, just to shop and compare. They write something like this. I would have to explain, actually I'm pretty sure I couldn't do this to high school students unless they were in detention for a long time. This ends up there, okay? But I'd have to explain a covariant and contravariant tensor. I'd have to explain, we'd have to do some tricky note keeping to realize what happens when you reverse those together. I'd have to do the same down when they're written down below, and then I'd have to show you how to crunch all that stuff together. I've done that. That's the way it's taught in Jackson, and that's the way they teach it to everybody else. And I think it's just computationally difficult. That's easy. Okay, so I like easy. All right, but from here on out, though, we're doing standard stuff. Okay, there's you can take this home. All right, and not shock anybody. So we write out the E and B fields. We multiply them out, and then we Sudoku for the rest of them. So we write these guys out, square them up, and and we get all these terms here, and we notice who's positive. Well, the only positive guys are the B field guys squared. Everybody else is negative. That's fine. And so here's a case where we're cloning now. Now, these are the B fields, and that's the E fields. And, okay, so these guys are all minus. Oh, yeah, that's right. They have the same sign. They should all be the same. And this guy, he's the B field, and he has some sign mixing going on, so he's got different signs. And since it was B squared, that makes sense. All these signs make sense. And really, it's just a game of Sudoku. Okay. So, but the Lagrange density is a little different. There are two small but important changes. One is we throw a factor of about half in there. Because if you take the derivative of B squared, you're going to get a 2 down there, and we don't like that 2. We're just going to get rid of it by throwing a half in front there. And then we need a current coupling term. This is the JA sort of thing. And I'm writing those as quaternions, and all we need for this thing is the scalar. And I should say, you know, I do research, so I think, well, what could I explore if I had infinite resources? It's like, well, the vector of that seems perfectly fine object. I bet if you did the vector of that, it would mean something. I think it would mean something that was really difficult. So I haven't waded into those waters yet. But what's cool is quaternions give you a place to go. It's like the vector, that should be important too. All right. So, but I'm not going there because I don't need to derive the Maxwell equations. So that's the picture of it, and we see we've got our B's on one side, we've got our E's on the other. And that is our Lagrange density. That's every way that energy interacts in a volume. So here again, we're going to start easy. We're just going to start on phi, and all we have to do is pay attention to the tail end of that. Everything else we can ignore. Which makes sense, right? Because B fields don't have any phi in them anywhere. So we can't use any of the B, and it turns out that out of the 3 terms, only those last 2 matter. So we've got 1 current coupling term and 6 derivatives. Sorry. Oh, I hit the wrong button. Bad button. All right, so there we are. Sorry. 1 current coupling, yes. All right, so now we start doing the taking calculus, and it's like, oh, we got the mixed term thing in here again, okay, but we also have squares, and the squares just kind of bring us back. So we just get this the x's. So all the square terms are really easy. And all the mixed terms, well, they're not that difficult either. At least it could be far worse. Okay, so when we go ahead and do this, we take the derivative with respect to phi, and that gives us rho. It's like, oh, another easy bit of calculus. And here we go, oh, we get that mixed term sort of thing, and we get one of these pure terms, and a mixed term, pure term, mixed term, pure term. So, okay, that's pretty good. And you go, oh, that is Gauss. We got Gauss. We got Gauss, and that is good. Okay. All right, now for Ampere's law, again, we're using the same Lagrange density. We're just using different terms in there, which is really cool. Okay, so it's all and you'll notice I picked out everybody who's got an AX. And it's a situation where there are just 2. There are just 2. There are just 2. Okay? But you go, oh, this crosses the great divide between what's on the B having to do with B, what's having to do with A. And so when I was thinking about, well, how do I explain which one is which? You know, it's like this has got this shifty thing going on. I bet that's a curl. Okay? That's kind of the way I get it visually, that's really a curl. Can you crank through and go, okay, that is a time derivative of the E field. I think that one's pretty easy, the time derivative of the E field. This one, I think you simply have to memorize, okay, or maybe figure out something cuter than I have. Because who knows the curl of something? Okay? You've got to be pretty hardcore to know that. You could believe that's the curl of something. And it turns out to be minus the curl of A. But that's something you just have to crank or I don't know. So anyway, so this is the EX. We're taking the curl of B, and we're taking the time derivative of E, and so that is Ampere's law, right there. And so Gauss is only about the E field, and Ampere is really about both of these things. And this is my trying to summarize all four in a graphical way. We've got our two Lagrangians on top. We've got the E dot B, so B and E are sitting right next to each other, or they're nicely separated. Okay? And then we have to go through the Euler-Lagrange mechanics, where when we got these identities, we saw the cancellations happening across the lines. And then we had Gauss's law, which was only E field, and Ampere's law, which was curl of B and the time derivative of E somehow being the current. So that's it. You now know how to get to the Maxwell equations, all four of them, in a formally precise way. So that's very good. At least I hope he feels good. I hope you aren't going to hunt me down afterwards.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the gradient